Hello, everyone. This is the last recorded lecture of the semester. It's crazy. We're almost done. So this lecture is from a workshop that I gave a couple years ago. It covers a lot of things that you don't really need to know specifically for the class. But if you are really interested in mediation analysis, this should cover a lot of that. For this lecture, though, we're going to just focus on the stuff that's necessary for the class. So reach out if you have questions about any of these parts or the other parts we don't cover. Feel free to watch this video. I think it's a really interesting one, but we won't watch it here. So today we're going to talk about what mediation analysis really is, how we interpret it. We won't really cover the current issues and solutions so much. Those are a little bit more advanced. They're definitely things you could learn, but you don't have to for this course. And then the last thing is, how do we use it? And that's in R. I'll show a few examples in the slides here. And then, of course, there's the examples tied to the class as well. When it comes to mediation analysis, this is a really common way of drawing it out. So you have X, that's your predictor or independent variable, all those. You'll also hear it called exogenous variable. When you see the word exogenous, that means it is not caused by something tied to the model. So it's from outside the model. Whatever made X happen, it is not related to this model. It just, according to this model, it is just how it is. M and Y are both called endogenous variables. They are caused by something else in the model. So if you see those words, that's all they're trying to say. You can have lots of different types of models that use these terms that look a lot like mediation but aren't exactly called mediation. The stuff that we talk about today should apply pretty well to even those other types of models. So we have X, it's a predictor. M up top is the mediator, and then Y is the outcome. Mediation analysis is trying to understand how X affects M that then affects Y. So path A is saying this is how much, if we change X, this is how much it changes M. And then the B path is how much does Y change when you change M by 1 unit. And then you have this C prime path, which is called the direct effect. It is the ways that X affects Y that's not through M. It could be direct, that X just directly affects Y in some way, or it could mean that there's other mediators that we haven't accounted for in this model. We'll talk about that a little bit more in some examples we give later on. It's really important to understand the difference between mediation and moderation. So mediation is how the effect of X is transmitted through M to Y. Moderation, what we've used already, which is really just an interaction, it's how the effect of X on Y depends on the level of the moderator. So these two diagrams hopefully help you see how this is playing out. So this one over here on the left is saying X affects M, which then affects Y, where the diagram for moderation is saying X affects Y, and the moderator affects how X affects Y. So X doesn't affect the moderator at all. They're essentially independent of each other. They move however they want to move. X is not changing the moderator. Rather, the moderator is just changing the effect of X on Y. So mediation analysis, this is really important that it's built on theory. The assumptions become more when it comes to the causal interpretation of the model. the assumptions statistically are very similar to regression. And that's because it's built up of 2 or more regression models. So it's really just regression under the hood. We're just using it in a certain way that allows us to get more information. Mediation analysis actually can be combined with moderation. So you can have a mediated moderation model or a moderated mediation model. It can get really complex depending on what theory in the prior literature and even expert judgment might suggest. Importantly, it helps us explain how X affects Y. Often we have something like an intervention, and we see that it's somehow helping this outcome. Mediation analysis helps us understand, how does that actually happen? In what way does it actually play out? How does our intervention end up affecting Y? What's also cool is it provides additional targets of intervention. So if we have some issues where we can't really affect the ultimate cause, the X, maybe we can help someone with M. I'm going to kind of show what that looks like in a minute. But it allows us to have these other places where maybe we can help so that the outcome is better. It also can help explain strange results. Sometimes you have some kind of strange or conflicting results, and mediation can help outline why those results are happening. It also provides a more holistic view of the relationships. It tells a more complete story of what is actually happening. So I emphasize built on theory, and the question might be, why even mention it? Well, mediation analysis has similar assumptions to regression, but they're somewhat more pronounced in mediation. So we've talked about no omitted variables. It becomes even more important that we're not leaving anything out when it comes to mediation analysis. We also really need to emphasize that the measurement error is going to affect the mediation analysis in different ways. For example, if we have measurement error in our mediator, it's going to make it look like the effect of X on Y through the mediator is smaller, and the direct effect is bigger than it really is. As such, measurement error can actually affect multiple parts of the model in potentially surprising ways. Of course, the well-behaved residuals and the correct functional form, those are still there. All these assumptions that we have with regression are still there, but the omitted variables and measurement error can be more problematic in mediation. Sometimes these are difficult to assess and correct, especially the no omitted influences. It's really built on theory, deciding what else is supposed to go in the model, what things are we supposed to control for. So when it comes to no omitted influences, there's 2 main principles you need to keep in mind. If something is related to X or M and Y, it needs to be in the path BC prime model. I'll talk about what that means in a sec. If something is related to X and M, it needs to be in the path A model. So if we go back to this, we can talk about the different models that actually make up the mediation analysis. The first model is where X and M are both influencing Y. So we look at Y. It's one of our endogenous variables, one of our variables that are being influenced by other variables in the model. And we look for all the arrows coming to it. And in this case, we have 2. We have one from M and one from X. So all those arrows that are going to Y, that's one model. In this case, it includes path B and path C prime. Another one of our endogenous variables is this M variable. And we look for all the arrows coming to that one, and all we see is the arrow from X. So that's another model, is just X predicting M. That means in this case, with this mediation model, there are two regression models that make up the whole mediation model. So if we come back to this, if something's related to X or M and Y, it needs to be in the path BC model, the model predicting Y. And if something's related to X and M, it needs to be in the path A model. This goes back to our elemental confounds idea, where you have the fork and the pipe. So we need to think about all those in relation to this. So if it is a collider, it's related to X or M and Y in a collider sense, and we do not include it in the model, but all the other ones we would. Something like an example to consider, if we were assessing religiosity, that's our X, and heavy drinking behavior, Y, what might be some variables that should be included? What are some things that may be related to religiosity and heavy drinking behavior? And we can go back to the elemental confounds and think about all these things, the fork, the pipe, the collider, and the descendant, and think about any variables that we can think of that are related to both of these, and decide what type of confound it is. And if it's any of them except for the collider, then we're going to include it in the model. For this example, some things you might have thought of could include, if we're looking at maybe adolescent or young adult religiosity and heavy drinking behavior, maybe we want to know what their parental religiosity is or their parental drinking behavior. Both of those could, in fact, cause both religiosity and heavy drinking behavior in a child or an adolescent or a young adult. And in this case, it would probably be the fork if we were talking about parent religiosity or parent drinking behavior. And so we'd want to include that in the model. So there is a slight caveat to all this. If X is randomized, in other words, there's like a treatment and control, so we're doing an intervention, then statistical theory says no other variables are related to X, which means we don't need to control for anything in the path A model. However, we cannot randomize M, at least in a single study. You can't do that. So even if we can get a causal relationship from X to M and X to Y, we cannot obtain a causal relationship from M to Y. That is, without controlling for everything that needs to be controlled for. Again, no measurement error. There's always going to be some, which means our estimates are going to be slightly biased. And I mentioned that it can be more pronounced in mediation analysis because it affects multiple paths when there's measurement error in, say, like the mediator. For the workshop, we reviewed linear regression here. Hopefully you remember a lot of the stuff about linear regression. So mediation is just two or more regression models. When it comes to mediation, there's two general frameworks. There's the ordinary least squares and GLM approaches that we've talked about in this class. There's also the SEM approaches, the structural equation modeling that we hinted on in chapter 18. I'm going to present both in this chapter just a little bit. I'm not going to highlight them in detail, but it's important to know that they're very related but distinct approaches. When it comes to OLS and GLM regression, you're fitting multiple regressions fit separately and then combined together. And it provides great flexibility. The assumptions are generally lighter overall than SEM. Provides model fit for each submodel, but not the entire model. And you can have continuous binary categorical count, proportion, and other variable types in there. just like you can with GLMs. For SEM, the multiple regressions are fit simultaneously. It's all together. The assumptions are slightly more restrictive. Generally, you need a bigger sample size overall, but it provides more information regarding the overall model fit. How does this model look compared to the data? And generally in SEM, you're usually working with continuous variables, but it can handle binary, ordinal, and some other types in some cases. You just have to specify that specifically with SEM in different ways than what you would in OLS or GLM. Two examples of mediation analysis used in the wild. Ford and Hill used adolescent religiosity as the predictor. It had three mediators: conservative respondent attitudes towards substance use, conservative peer attitudes towards substance use, and depressive symptoms. And its outcome was substance use across a number of substances. So what they were hypothesizing is that your adolescent religiosity impacts these mediators. It changes them in some way. So if you're more religious, you're more conservative towards substance use. Your peers are probably going to be more conservative. And in some way, religiosity is going to affect depressive symptoms. All of those, in turn, are going to then affect substance use. Another one with Wong and Brower, you have sleep problems as the predictor, and that affects alcohol-related problems, drug use, and depression, which then affects suicidal thoughts. In both of these, you can see how a main predictor, something we're really interested in, we know that sleep problems ultimately affect suicidal thoughts, but we may want to understand, how does that happen? And one reason why we want to know why this happens is we may want to know, well, in some cases we may not be able to help with sleep problems. There may be an underlying biological issue that makes it really tough to help with sleep problems. But maybe we could intervene in alcohol, drug use, or depression areas. And if we were to help there, in turn, it would reduce suicidal thoughts. This is nice because it gives us more areas that we can say, oh, we can't intervene here, but maybe we can intervene here and ultimately help in this outcome. At this point, you may be wondering, so how do I actually interpret the results from the mediation? In general, there's lots of things that come out of a mediation model. So you have the individual path estimates, which are just regression estimates. Then you have the indirect effect estimates. You have the direct effect and total effect. So the individual paths are just the A, B, and C prime. Those are just like what we've done with regression. The indirect effect is the A path times the B path. And from there, the interpretation is a lot like regression. It's saying X has this effect, whatever A times B is, through M. So we'll highlight that better in just a moment. The direct effect is the C prime, and then the total effect is the indirect plus the direct effect. Notably, many resources suggest ways of looking at this where you should just say, is it complete or partial mediation? This is just an estimate looking at, is the direct effect significant or not? I don't recommend focusing on this, but you can always check. It's always based on whether C prime is significant or not, while the indirect effect is significant. But the issue with it is that it paints an incomplete picture of the model, because if I just say, yes, there was complete mediation, one issue with that is it's just looking at the C prime path and saying if it's significant or not. So it's just focusing on significance, not effect sizes. And to really make this conclusion, we need really large sample sizes to be able to say that C prime is truly small or non-existent. If we have a small sample size, then we might get a non-significant result, but that's just because we don't have enough power in our model. And in my experience, it's almost always partial mediation. You never really truly have complete mediation. There are some cases you certainly can find that, but generally that's really rare. At this point, the slides go over some things referring to the types of mediators and outcomes. And if you're interested, it goes into a lot of depth of how you can handle these situations. But we're going to jump into actually how we use mediation. Before we actually get into the syntax, there's some good books on this if you're interested in learning more about this approach in general. There's Statistical Mediation Analysis by McKinnon. And there's an Introduction to Mediation, Moderation, and Conditional Process Analysis by Hayes. Same author of the book that we use in this class. Those are really good. When it comes to mediation analysis in R, there's generally two approaches, just like we talked about using Levon, and then there's one that I developed. It's called Marginal Mediation. We'll quickly go through both of those. We're going to use the Office Parks data set that you've seen before in this class. Whenever you're doing mediation or any analyses, you always want to do cross-tabulations. You want to check for small cells. You want to understand your missingness, where things missing, stuff like that. You also want to check for high correlations, as these can cause multicollinearity problems if you're looking at covariates. It also can be really good to know across the board what the raw correlations are in any analysis. When using the SEM framework, we use Levon in R. It's the best one for the most part. There's some other good ones, but Levon is the most complete. The way that we do the model here is we create a model object that is just text. So we have a quote on the front and a quote on the back, and then here what we have is we are basically doing a regression very similar to what we've done before, but now we're adding a times and a star times subs. In the SEM framework, what this is doing is it's making the estimate on subs predicting productivity and makes it labeled as A. You could put any word there. It's just a label for that path. And then, so we use A here because that's the common symbol for that path. And then we have income predicted by productivity and substance use. And so we have B times and C1 instead of C prime because prime is not one that R likes to have in a name. Just looking at what I have here, these two lines of code, are you able to see what the mediation model actually is? So one of the first things you want to look for is what is our mediator here? And in this case, our mediator is prod1 because it is the outcome in one model and a predictor in another. It can't be income because income is an outcome here, but not a predictor in the other model. So this one is our mediator, this is our predictor, and this is our outcome. The reason why we named these is it allows us to create the final estimates that we may want to get out. So we use this colon equals operator to say we want to create another estimate that it will use from information from these models. And the indirect is just A times B. The direct is just C1. And then the total is the indirect plus the direct. And then we close it with the quote. So this is just text to R. And then we plug it into the SEM function. So the model is all of this information right here. And we just tell it the data where it's coming from. And in this case, we're just saving it as fit SEM. We can get our parameter estimates out. We can get our fit measures out. We also can just do summary of fit SEM, and that will give us all this information as well. If we do the parameter estimates, it gives us all of this, quite a bit of information. If we're interested in our indirect effect, we can go straight here and see our indirect effect is negative 12.1. And it looks like it is significant. And here is our confidence interval of that effect. Same with our direct effect and our total effect. In other words, we're saying the effect of substance use on productivity and the effect of productivity on income together is that much. Substance use directly on the income is this, and that's not significant. And the total effect is this. Then we have fit statistics. When you get into SEM courses, you're going to talk about these in a lot of depth. They're just saying how much the data fit the model that you specified. How well do those actually go together? You can also use the OLS framework. This is going to look a lot more like what you've used before. In this one, we're going to use the marginal mediation package. In this one, we just create all the paths. So we create the path A model and use GLM. So we're just going to say substance is predicting productivity. And the path BC is this one, productivity and substance predicting income. And then we use the MMA function for marginal mediation analysis. And we put the path BC first and then all the path A's if you have multiple. And then you tell the indirect effects. In this case, it is substance through productivity. And then OLS, this framework uses bootstrapping, and so this is how many bootstrap samples we use. 500 is a good start. You wouldn't want to go much lower than that, generally. And the output, it's going to give you the regressions that are part of this. And then it's cut off on this slide, but it's going to give you the indirect and direct effects as well. Before we get into some final things, what I want to highlight is what this number actually means. In this case, substance use is dichotomous, so it's just 1 or 0. And in this case, that would mean those that use substances have an income that's about 12,000 less, where that effect goes through productivity. So if we're looking at how substance use affects your productivity, which then affects income, it looks like substance use affects income by about $12,000 through productivity. It affects it by about 7,000, almost 8,000 directly, even though this is insignificant. And overall, the total effect is about 20 grand. So if you use substances, overall you earn about 20 grand less. And 12 grand of that is because substance use lowers your productivity, which then hurts your income. Hopefully that's making some sense. We also want to do diagnostics on our models. In general, it depends on the type of model. So if you use SEM, you're going to be looking at slightly different things than if you use OLS. But overall, we're still going to look at model fit, which is R squared or BIC. We're going to want to consider multicollinearity, which would mean if X predicts M too much, if they're too related, then your path BC model is going to have a problem with multicollinearity, which is kind of interesting, which usually means that your mediator is so related to your predictor that they're kind of the same thing, which is interesting. And that's really it for what you need for this class. Reach out if you have questions. This is a whole topic for entire books, and so if you're interested, reach out, look at those books, and see what situations you're probably going to use it in, and we can talk about that.